So welcome to, I don't know how many we've done so far, so just welcome to Mount Cuba's virtual public nights. Tonight, Connor Mooney is going to do your presentation. He is a student at the University of Delaware, and we're excited to have him with us this evening. We're going to do like we normally do. I'll have everybody mute themselves. If you have a question during the program, put it in the chat and I will politely interrupt Connor to give him any questions that you have. If you want to wait and hold them till the end, you can do that as well. However you choose to do that. And with that, Connor, I will go ahead and turn it over to you.
So thank you for that introduction, Kim. My name is Connor Mooney. I am a UD student. I'm a second year graduate student in physics and astronomy. So I hope to sort of shed light on this kind of complicated topic, just through the history and a little bit about the morphology and certain things about what an active galaxy actually is. Let's get started. Start at the beginning. Back in the year 1943, Carl Seifert discovered about 6 nearby galaxies with bright nuclei that have broad emission lines that he coined Seifert galaxies. So again, I'm not exactly sure how in depth to go with this talk, what the audience's level is, but here on the right, we have our emission spectrum, which basically dictates brightness over wavelength. And we see these lines or peaks that correspond to specific emissions of light due to hydrogen or other atoms, other elements. So specifically at this wavelength of 6,550 angstroms, we can see that this emission line is not really a line at all. It's actually a fairly broad peak. We expect these to be more like a line. So that first galaxy discovered was Messier 77, shown here. This is not the nice picture he saw, of course. This was taken by the Hubble Space Telescope, as most of the images in this presentation are. Okay, so what does that broad emission line mean? Well, broad lines indicate something called Doppler broadening. This is when the speed of the emitting object has to be very high, and it's either coming close to you or away from you. So Doppler broadening is a lot like the Doppler effect. In this case, we are talking about light, though. So we know that light obviously has a particle and a wave. It can be one or the other. And if this light emitting object is moving towards you, then the peaks of the wavelength become closer together. If the object is moving away from you, the distance between the peaks of the wavelength of light will increase. So, right, longer wavelengths is called redshift, shorter wavelengths is blue shift. I think most of us are well aware of that. Basically, the gas in the nucleus of this galaxy must have speeds between 1,000 and 5,000 kilometers per second close to its nucleus. Some of the gas is moving away from us, some of it is toward us. That's why we have a red shift and a blue shift, both directions. That's why our emission line broadens both to the left and the right. Okay, so to give you a concept of how fast that gas speed is, the spiral arms in the Milky Way move at about 200 kilometers per second. And our local group, which corresponds to about 30 galaxies, moves at a bulk speed of about 1,000 kilometers per second. So this is extremely fast, extremely high temperature nucleus. Okay, so development in radio astronomy in the 1940s and 50s led to the discovery of something called radio stars. This was the next sort of active galactic nucleus that they didn't know what to call at the time. These were called stars because they were perceived as point-like objects emitting these giant, and I mean giant, large radio lobes at both sides, both ends from this point source, basically. Okay, so this is Cygnus A. This is 600 million light years away, which is significantly far. But it has a mass of 2.5 billion solar masses in its supermassive black hole. To give sort of context, the Milky Way's supermassive black hole in its center is about 4 million solar masses. So these lobes that we see, these large radio lobes, correspond to a distance of about 300 times the diameter of Andromeda Galaxy. So despite the fact that this is extremely far away, these lobes are so large and bright that we're able to see them all the way back in the 1950s. Another famous active galactic nucleus that they didn't know what to call at the time was Centaurus A. This one, although not nearly as bright, is much, much closer. Instead of what, 600 million light years away, this is 14 million light years away and about 1 million light years across. So that corresponds about 4 Andromedas if you put them back to back. What's interesting about this, though, is if our eyes could perceive light in this range of wavelengths in the radio range, then this image in the top right is actually what we would see in the night sky. Okay, its angular separation is 8 degrees, right? So the moon is about 1/2 degree in angular distance, and the length of Centaurus A is 8 degrees. Each lobe outputs about 20 million times the energy that the sun does over its full spectrum at only one wavelength of, or one frequency of 1.4 gigahertz. That's some radio frequency. Again, the nucleus itself is unresolved, and by 1958, they decided to coin the term active galactic nucleus to describe all these different types of confusing objects in the sky. And the term active galactic nucleus, just that concept became a key component in theories of galactic evolution from then on. So let's go over what they did in the 50s and 60s to estimate like the size, the duration, like the lifetime, and the mass of these active galactic nuclei. So I believe this is volt year. In 1959, began to make the first.
I'm sorry to interrupt you. We did have a question before we
Okay.
go too far. The question is, what matter comprises the lobes?
Yes, that is a great question. What matter comprises these lobes? Mostly electrons, all charged particles, basically. These lobes are due to charged particles moving near the speed of light, typically from something called synchrotron radiation, which I'll get into a little bit further on in the talk. But yes, it's cosmic rays, charged particles moving near the speed of light. Yep, good question.
Thank you.
Mm-hmm. So the first estimations of size of an active galactic nucleus is actually very crude. So basically, how do I say this? The Rally Criterion is something that we all might know and love that basically relates the resolution, right? How detailed an image looks to the wavelength that we're looking at divided by the diameter of the telescope that we are observing with. So at the time, with what technology they had, the smallest spatial resolution that they could come up with was about 100 parsecs, or 326 light years across. Just to give like a little bit of intuition of spatial resolution, I have 4 images here, the rightmost one being from the Hubble Space Telescope, and these are from worse telescopes. You could imagine that if, let's say, this central white blob here was the active galactic nucleus, then if our telescope was only as good as this leftmost image from a much cruder telescope, then the best we could say is that the how do I say this? The minimum distance that this active galactic nucleus spans would be this whole wide 100 parsecs, even though in reality it could be much smaller. Okay, so now let's estimate the duration, the lifetime of these AGN. So sort of like Carl Sagan would use logic to try to explain different things in the universe. This is what our guy Voltaire did. So the logic goes like this. Seyfert galaxies make up about 1 out of 100 spiral galaxies in the universe, about 1%. And we know that the universe is about 10 to the 10 years old, about 10 billion years old. So we have two extremes in this logic. One is that a Seyfert galaxy, that is its one and only phase. It doesn't transition into any other morphology. So once a Seyfert, always a Seyfert. That must mean that the age of that galaxy is about the lifetime of the universe, 10 billion years. The other extreme is that all spiral galaxies must pass through a Seyfert phase at some point in time. So in this case, if about 1 out of every 100 spiral galaxies we see is a Seyfert, then the Seyfert phase must last on the order of about 10 to the 10 divided by 100, or 10 million years. So what this is saying is that nuclear emission in an active galactic nucleus must last longer than about, did I say that right? 100 million years. About 100 million years is the minimum amount of time that an AGN exists. So these are long-lasting objects, which is great, which I'll explain in the future. Finally, let's estimate mass. There's something called the Virial Theorem, which relates the total kinetic energy of a self-gravitating body, meaning some sort of body where it holds in all of its mass and energy. So it relates that total kinetic energy of the body due to the motion of its constituent parts, right, the gas and the stars, to the gravitational potential energy of the body. And it's a very simple theorem, complicated to derive, but it's basically saying that 2 times the kinetic energy of the system is equal to the gravitational potential energy of the system. Okay, so if we say that the kinetic energy is the mass of the galaxy times the average velocity of the gas squared divided by 2, right? 1/2 mv squared. And we say that the gravitational potential is about g, the gravitational constant, times the mass enclosed squared over the average distance between objects. Then we can rearrange this to say that mass is velocity squared times the size of our object divided by this gravitational constant. So if we take the upper limit we had before, 100 parsecs, we take the average velocity, which we got from Doppler broadening effect, and our gravitational constant, we can say that the upper limit of the mass is about 10 to the 10 solar masses. Okay, so very massive objects, clearly. So right here on the right, we see an actual image of an active galactic nucleus. Just kidding. There are no actual images of an active galactic nucleus. Even today, they are much too small. They're point-like. They still look like stars. Hence the name radio stars we talked about before. Here on the left, here is the basic structure of an AGN. We have some torus, some cloud that is shaped like a donut of colder gas and dust. And due to the fact that in an inertial frame with no external forces, right, a contained system, we know that conservation of momentum is a thing. Conservation of angular momentum is a thing. Basically what I'm saying is that as this cold gas and dust falls towards the center of this AGN, towards this supermassive black hole, it will necessarily have to gain speed to conserve angular momentum. So as it gains speed, it becomes hotter. There's more friction between this gas and dust, up to the point where it ionizes this gas and dust. And then this rotating disk called the accretion disk will create its own magnetic field perpendicular to the face of this accretion disk itself, right? It'll shoot out from both ends of the black hole. And then there are these other regions that just exist because they have to, right? We make observations and we say, oh, these lines are broad, so there's broad line regions. These lines are narrow, so there has to be narrow line regions. But the basic structure is we have an accretion disk, a supermassive black hole, and then these jets of charged particles that exist due to strong rotating magnetic fields. Great. So what about the size of an AGN? So a simple way to measure the size of an AGN is to know its distance and take that distance and find its diameter. And then, well, of course, if you have its diameter, you would know its size. So our nearest known AGN is NGC 4395, shown in this nice Hubble image to the right. It's 14 million light years away. It is still unresolvable from the Hubble Space Telescope. Okay, Hubble's resolution is about 0.05 arc seconds. I should have that in degrees. That is much, much smaller than a degree. I'll do the math later. This must mean that this galaxy has a diameter of less than 1 parsec. So if we take this simple equation, we say that our angular resolution is 0.05 arc seconds times the distance away, 14 million light years. This must mean L, the linear diameter of this AGN must be less than a parsec. Still, we can do better than that. There's another type of study that we're able to do to constrain the size of this compact, what we now are beginning to see is a very compact region in the center of a galaxy by variability studies, how much flux or brightness, measured brightness, changes over time. So an AGN, especially the brightest ones, the ones that I do research with, are highly variable. Different wavelengths, like the amount that it varies, differs based on whatever wavelength you're looking at. But typically the higher wavelength you look at, the more the flux or the measured brightness will vary. So here's an example of another AGN, MCG 63015, which varies, as we can see. This is time and this is brightness, right? It shows brightness over time. It varies over thousands of seconds in this specific wavelength, the X-ray waveband. Okay, so the smaller the time scale, or the more it varies basically over time, the greater you can constrain the size of an AGN or of any light emitting object. So how does this work? A good way to intuit this is with the lampshade analogy. Basically, it goes like this. Okay, we have an emitting source, this light, that diffuses over this region all the way up to this lampshade. So this spherical lampshade is basically our emitting region in this case. If we're observing to the right here, then this closest point to us, it will take time t0 to get to us. The farthest emitting point from us that we're able to observe would be here at the bottom. It will take us this time t0 plus some extra, very slight amount of time. It's not so slight, but in terms of like on a cosmic scale, it's not slight. On a small scale like a lampshade, it's obviously not detectable by the human eye. Okay, so this time delay term, this extra term, We relate it by the size or the radius of this lampshade divided by the speed of light. Okay. Right, we know that speed is distance over time. If we rearrange that, we're saying that time is distance divided by speed. Okay. So what is this time delay for a lampshade if this lampshade was as big as Earth's orbit? Earth's orbit, like 1 astronomical unit, is 1.5 times 10 to the 11 meters. What is that? That is 150 billion meters divided by the speed of light. That would be 500 seconds. That means that if our lampshade was as big as Earth's orbit around the sun, the closest emitting region to us would get to our eyes 500 seconds before the farthest emitting region. Okay, so we can apply that to things that are much further away as well. So if we take our time delay or time scale for variability to be the shortest, this is a typical unit of measurement that we do for variability studies. It's the shortest amount of time for our flux or our brightness to double. Okay, so let's say we take this bottom point here. That's about 0.5. It's about 0.5 photons per second. That means 1 photon every 2 seconds. Okay, so the amount of time it takes to double from 0.5 to 1 looks to be about 1 interval here, which is, what is that, 1 interval, 2 intervals? That's about 10,000 seconds. Okay, so if we take a time delay of 10,000 seconds and multiply that by the speed of light, like we did here, we can say that our emitting region is about 20.6 astronomical units, or, an astronomical unit is the distance between Earth and the sun. That also corresponds to about 3 light hours, or the time or the distance that light could cover if it moved for 3 hours. This is smaller than our own solar system. This proves that active galactic nuclei are extremely compact, so much so they're even smaller than our solar system, which on the scale of galaxies is extremely small. So we know that they are very bright, they're very dense, they're extremely compact. There are other signatures to indicate that it is also an AGN. Another indicator is that it is emitting light across the entire electromagnetic spectrum, all the way from radio to the highest gamma rays. Okay, so here's a scary looking plot that I am not getting too much into. This is actually the simplest plot of an AGN that I could find that describes what I want to talk about. So this is basically, again, this is flux or measured brightness over high level. Okay, this is brightness over frequency, right? Frequency is sort of the inverse of wavelength. It's basically a spectrum, brightness over the electromagnetic spectrum. And the point is that a typical star will peak in its brightness around the infrared and optical band, and then will quickly drop off. But if we trace out an active galactic nucleus's spectrum, it'll start strong, it will go up, and it will continue to be strong all the way up until gamma rays, or very high energy gamma rays. Yep, so that's a strong indicator that it is an AGN. AGN have thermal and non-thermal emission regions. As someone asked before, what was the actual source of those plumes of radio? Like those radio plumes, those were due to non-thermal emissions. Okay, so the brightest AGN out there are called quasars. I think a lot of people have probably heard the term quasar. A lot of terms sound the same in astronomy, so I'm sure I was confused at some point as well. A quasar is named, it's kind of a misnomer. It was coined in 1963 by Martin Schmidt, and he coined it a quasi-stellar radio source. Again, it's quasi-stellar because it looks exactly like a star would. The only difference, well, is all the things I've talked about before. It emits light over the whole electromagnetic spectrum. It's extremely bright, things like that. So here's an example of another AGN 3C273, whose hydrogen emission lines were shifted over by more than 1,000 angstroms or 100 nanometers, if those sound familiar. Those are units to describe wavelength. Something that is shifted, redshifted, indicates that it is further away. So if this hydrogen emission lines were shifted by 1,000 angstroms, this corresponds to a redshift of about 0.15. And as a lot of us may or may not know, something that has a higher redshift is further away, typically, due to the expansion of space over time. So this means that 3C273 is about 2.4 billion light years away. So in 1960s, people were very confused. How can something be that far away and we can still observe it? Like nothing has been observed 2.4 billion light years away before. Is it truly that luminous? The answer is yes, quasars are exactly that luminous. They're the most massive and luminous subset of AGN. The brightest, the most, how do I say this? The brightest, most consistent source, I would say, in the universe would be quasars. This specific one, 3C273, is 1,000 times the luminosity of the Milky Way and smaller than the Milky Way. So quasars, because they are so bright, we're able to see them extremely far away. The farther away that we look in space, the farther back in time we're looking, right? So therefore, the oldest objects in the universe that we're able to observe are in fact quasars. Therefore, they are one of the best probes, I would say the best probe to look into the early universe. And this plot here is just showing the estimated amount of quasars over the time of the universe existing, peaking around 3 billion years. Orientation matters though. There are technically more energetic, there's a more energetic categorization of AGN called blazars. These are the same exact thing as quasars, except that they are oriented in a different way. They're the same, all the same emission regions exist. Everything about it is the same, except that the face of this accretion disk is pointed directly at us. Okay, so these jets that I've talked about are pointed directly towards us, and we are being showered by charged particles from these jets. Not a lot of flux, especially at higher energies, but very bright emitting regions. So again, these are quasars whose jets are pointed directly towards Earth. In this case, blazars are dominated by non-thermal emission or non-thermal radiation, which is, I believe I already said it, but it's emission due to charged particles, not due to the heat, like the sun, or radiation, thermal radiation like the sun, but due to particles accelerating and changing trajectory, it will emit light. Why does something pointed towards us versus like perpendicular to us result in a brighter, like a higher brightness? This is due to something called relativistic beaming. This is an effect, this is a relativistic effect due to the fact that these particles are moving in the speed of light, near the speed of light, not at the speed of light. In the frame of the charged particle emitting light, it appears to itself, it is emitting light in all directions. But from an outside observer, you'll notice that the intensity of light collimates in the direction of movement of these charged particles. So if these jets are shooting directly towards us, the light collimates directly towards us and increases the apparent brightness, the brightness that we observe. So blazars are the most consistently variable and energetic objects in the universe. The one that I deal with in my research is Markarian 421. This is, I believe, the second closest blazar that we know of, but it is extremely bright. It might be the brightest blazar, and it's highly variable with no standard luminosity value. It's being extremely close is 434 million light years away, which in terms of quasars isn't very close, but it's very rare to have a quasar oriented directly towards us. So this is actually as close as we're going to get with a blazar, 400 million light years away. Markarian 421, along with every blazar, has a low energy peak and a high energy peak. So what do I mean by that? Here again, we have frequency on the x-axis, frequency of light, and then we have a scaled flux or brightness scaled in some way. The low energy peak is the brightness here, and the high energy peak is the brightness here. So what we're interested in today is what causes that low energy peak and that high energy peak to exist. What models can we use to explain that? Well, this low energy peak or low energy component is due to something called synchrotron radiation or synchrotron emissions. And the high energy peak, nobody can agree on. The most common and simple model is synchrotron self-Compton, which I'll talk about. Other possible explanations for this high energy peak here are something called a proton initiated shower, or external Compton, which is like light from just the cosmos, basically giving energy to light that already exists. But I'm going to focus on synchrotron emissions and synchrotron self-Compton. So here on the top left, this is an image of synchrotron radiation. Well, this is an active galactic nucleus, the accretion disk that we've seen before. Here's our rapidly rotating strong magnetic field. And what happens is primarily electrons will, because they're charged particles moving with high speeds, will have a strong spiral trajectory, right? If we know that a charged particle in a magnetic field will generally have some sort of spiral trajectory. Because it's spiraling, it is technically accelerating towards the central axis that it is spiraling around. Okay, so an electron is spiraling along an axis. It is accelerating towards that axis. And because it is accelerating, it loses some energy in the form of synchrotron radiation. Synchrotron radiation can be anywhere between can emit anywhere between radio waves all the way up into X-rays. There's a large spectrum that covers synchrotron radiation. In the term of blazars, especially Markarian 421 that I'm dealing with, that I'm biased towards, synchrotron radiation is emitted in the X-rays. Okay, so the synchrotron radiation is then, the energy of this light is increased through something called the inverse Compton effect. First, I want to say what the normal Compton effect or Compton scattering is. Compton scattering is fairly simple. It's just an incident photon will interact with some slow moving electron, and it will give energy to that electron, right? The electron will collide with it. It will increase its momentum, go flying off, and the incident photon will lose energy in the process because conservation of energy exists. Okay, so the inverse Compton is the opposite of this. Inverse Compton effect is when a low energy photon collides with a high energy electron, and it.
Connor, can I interrupt you for a second? I'm sorry.
Sure, yeah.
The question we have is where and what are the corresponding positive particles located to balance this large number of electrons in the jets?
Where do the protons exist, like to balance out the number of electrons? Is that the question?
I'll read it again for what
Yeah.
it says. Where and what are the corresponding positive particles located to balance this large number of electrons in the jets?
Well, if I understand the question correctly, I will say, I'll just explain that electrons have like a much smaller mass than a proton, right? So there's a much higher population of electrons in the jet itself, influenced by the magnetic field of the jet, whereas the protons themselves are much heavier and are much less likely inclined to follow the collimated jet's trajectory. So you'll find your protons more in these emitting regions near the accretion disk, whereas your electrons are the ones that are shooting out. I don't know about the actual like chemical composition of an AGN, but I'm assuming that it's so energetic. The temperature is so high in this disk that it's really just protons and electrons. So we're not dealing with helium or atoms. We're just dealing with protons, electrons, and then other subatomic particles like neutrinos and pions and things. So basically, yeah, everything loses its chemical composition and it's just protons and electrons that are being affected by the magnetic field. I hope that answers your question.
Yes, it did. Thank you.
Mm-hmm. Okay, so synchrotron radiation due to a spiraling electron, it'll radiate light perpendicular to the trajectory of the electron. And then those same high speed electrons near the speed of light will collide with those X-rays that it emitted itself, right? So an electron will emit light and then another electron will come by and upscatter that light, giving that light more energy. And that is called synchrotron self-Compton effect. The synchrotron radiation is boosted in energy due to this upscattering, due to its own particles. It's kind of like a self-contained boost of energy. And that is what theoretically explains the second peak here on the right. So in review of this, I just want to go over the 4 different sort of categories and subcategories of active galaxies that I've talked about. First were Seyfert galaxies. These are fainter active galaxies, or these are galaxies with fainter active galactic nuclei, right? Their nucleus is not as bright. Therefore, you're able to actually see the stars in gas around it. These have strong broad emission lines, as we saw in the beginning, and they're typically found in spiral galaxies. These AGN are found in spiral galaxies, whereas radio galaxies, the ones that we saw that had those giant radio plumes, those are typically found within elliptical galaxies. And like the Seyfert galaxies, we would expect its luminosity to be just the nucleus itself, not the entire galaxy. Just the nucleus should have between 0.1 and 10 times the luminosity of our entire Milky Way. Then we talked about quasars. These are brighter, more distant Seyfert galaxies whose brightness dominates its own galaxy. The nucleus is so bright that the rest of the galaxy is just outshined by it. Looks like a star, quasi-stellar object. And then finally, I talked about my favorite blazars, which are quasars with jets pointed directly towards the observer. These lack emission lines, and they have no standard brightness or luminosity because they vary so much. So they're highly variable and they have no standard luminosity. And here's some sources. Thank you.